Ladies and gentlemen, now we will start the first lecture of the case study module. The module has been divided in 2 lectures. The module includes the following documents for download: the course material in PDF, different types of data collection and analysis as Excel files, charts and figures. The textile industry is one of the largest industrial sectors in the world, and the challenges facing the textile industry with regards to providing sustainable growth, with acceptable quality, and production with high profit are huge. After the quality revolution, the textiles industry has started implementing the modern manufacturing paradigm, like Lean, Six Sigma, Total Quality Management, etc. The spinning mill is the first section of the textile industry. The output of the spinning mill is the yarn wound on paper, or plastic conical-shaped packages, called cones. The spinning mill consists of 6 stages: mixing, carding, drawing, roving, spinning and winding. Reducing variability is a magic solution to solve our quality problem in our project. Using Six Sigma tools, we guarantee reducing the variation in significant range and achieve the required quality level. Now, we will introduce the tools which have used in our project in the define phase. For review, during the define phase, we will define business drivers, customer critical processes. Also, we will define project and develop implementation plan. In order to understand the target from our project selection and determine the problem statement and goals, we will make a short introduction for the project environment. We made our case study in modern spinning factory. The factory are producing denim and fabric yarn with high quality for local and international market. We will work in the final stage of the yarn manufacturing, which is the winding process. In this process, the finished bobbin from the previous stage spinning process is converted from bobbin to cone. At the same time, any defective in the yarn is cut and replaced by controlled splice. The tension on the yarn in the cone is adjusted in order to achieve the required density for next stages. The most important critical factors in winding process is the quality of produced cones, which measured by number of good and bad splices, which done using splicer. Number of remaining faults in the cone, which controlled by yarn clearers and clearing limits. The package length and weight, which controlled by machine speed and process cycle time. The package density, which adjusted using the tensioner of the winding position. Our project has 2 objectives. First, to check and adjust the remaining faults in cone by control the number of cut-in winding machine using yarn clearers, and to control the tension of the produced cones. Second, readjust the winding machine speed and reduce the setup time in order to reduce the bobbins waiting to enter the winding process after finishing spinning. However, increasing the winding speed above a certain limit caused quality problem by creating faults in the yarn and affecting the final package shape. Problem statement is: high number of bobbins waiting for winding will reduce the productivity of both winding machine and spinning machine and increase the lead time. In addition, the quality of produced yarn after the winding process is not meeting the customer requirements regarding number of faults per 100 km produced yarn and the tension of the produced cones. Project goals are reducing the width by 50% by increasing winding speed in specific range, and reduce the variation between spindle without affecting the final quality, and reduce the setup time as possible in order to reduce the total lead time. Readjust the tension and quality of the yarn to fulfill the customer requirements. Reducing the cost of waste yarn with percentage from 20% to 30% by improving the quality of yarn produced in the spinning process. Reducing waste time of the spinning process, waiting for the bobbins from the winding process with 40% to 50%, which increase the productivity of the factory. Project team and stakeholder have been identified early to have a communication plan for each of them. The project team, which will join the project from beginning, production manager, quality manager, and quality control supervisor, maintenance manager, and maintenance engineer, winding machines operators and supervisors, spinning machines operators and supervisors. The stakeholder included all the above project team, mill manager, warehouse and finance managers, previous stages supervisors, the weaving stage supervisors and operators, the weaving stage quality control manager. SIPOC is a high-level process map, includes suppliers, inputs, process, output, and customers, which will be used to identify all relevant elements of our process improvement project before work begins. The supplier of the winding process are the spinning stage, the paper cone manufacturer, the spare part inventory, the maintenance department, the quality control department. The inputs of the winding process are the paper cones, the spinning bobbin, and spare parts for winding machines. The process steps are checking the operation of the machine, adjust the yarn clearers, adjust the tensioner, supply the finished bobbins to the machine, starts the machine, and collect the finished cones. The outputs are finished cones and empty bobbins. Customer is the weaving process. The voice of the customer is a process used to capture the requirements, needs, and feedback from the customer, either internal or external customer, to provide them with best-in-class service or product quality. Table lists the internal and external customers with their complaints, results, and action to do in our project. Weaving department is the external customer. They have two complaints: high number of faults in the cones, and the tension of the package is not adjusted. Results of the complaint are: each thin places and thick places can cause stoppage for the weaving machine for 5 minutes, and the produced fabric has lower quality. Actions to do are: improve and control the mean value and standard deviation for number of fault per 100 km of produced bobbins, and improve and control the mean value and standard deviation for the tension of each cone. The spinning sector is the internal customer. The complaint is long setup and production time of the winding machine. Results of the complaint is stoppage of the spinning machine for the high width bobbins. Action to do is reduce the setup time and increase the machine speed without affecting the quality. To collect the data, we use the interface connected to the winding machines and yarn clearers. Also, operators have counted some production data, like WIP, and some measurements have been done for the density of the produced cones and the number of remaining faults in the produced cone after winding. The details of data collection are in the measure phase. The Kano model is a theory of product development and customer satisfaction, which classifies customer preferences into 4 categories. The 3 current problems in the winding step of our project are shown in the model. Adjusting the tension of the package is a basic requirement, while number of cuts in the bobbin will affect the performance. Solving the problem of high number of faults will increase the satisfaction. In order to make the affinity diagrams, all the issues and claims that belong to the spinning, winding and weaving sections are displayed. Rearrange all the issues and claims. The shown affinity diagram is shown. For example, the previous processes are out of control, the quality of the input bobbins is not good, the quality of supplier is not good, full of water and oil, and quality of raw material is bad. All these issues are related to the quality department. The cleaning of the drum and winding machine is not good, machine efficiency is low, the operators need training, machine speed setting is wrong, and the production plan for spinning step and winding step is not adjusted. All these issues are related to production department, and so on. The purpose of critical to quality trees is to convert customer needs or wants to measurable requirements for the business to be implemented in our project, as illustrated. By the end of the define phase, we clearly clarify the action to do in the next step. For example, for the need of improve the quality of the winding process production, the driver's arm reduce the waste from the winding machine, reduce the number of faults passed to weaving process, and adjust the tension of the produced packages. The CTQs are improve the quality of the spinning process, improve the quality of the raw material, make the necessary maintenance for the spinning machine in time and quality, readjust the clearing limits for the winding machine, readjust the splicer installed on winding machine, and readjust the tensioner installed on winding machine, and package density. After problem definition and critical to quality determination, we will start the measure phase by doing the following. Measure key process, collect and analyze the data, then identify the vital few that have greatest impact, estimate process capability, and measurement system analysis. Data collection has been done using a special software called Duster Quantum Expert. It is a data collection software installed on a high-capability server computer and connected through local area network to the Uster yarn clearers, which installed on winding machines for 24 hours. It collects all the necessary data, such as number of cuts per 100 kilometers, production data for each machine, speed, stoppage time of each winding position, and also average speed for each machine. The table shows the data after importing to the Excel sheet for analysis. In addition, we did a manually data collection at the end of each shift, work in process between the spinning process and winding process, quality data for the tension and shape, in addition to the remaining faults of the produced cones from the winding machines. Measurement of the environmental condition of the mill for 24 hours per day have been done also. We will work on 15 winding machines, supplied from 15 spinning machines in the new mill. The produced yarn is carded with yarn count NE30. Each spinning machine will produce from 2 to 3 lots, each shift with 1,632 bobbins per lot. Each winding machine will produce from 2 to 3 lots per shift, with 60 cones per lot. The collected data are divided into two categories: data collected from machine interface, or clearers control unit, such as cuts per 100 km, weak places per 100 km, winding speed, and yarn break per 100 km. Data measured by operator, using a measurement tool, such as yarn tension, and package density. Measurement system analysis should be done for the data measured by operators using measuring tools to determine if a measurement system can generate accurate data. We calculate the measuring system precision to determine the error due to gauge or operator variation. We calculate gauge R&R ratio. The ratio should be less than 10%, or an action should be taken for operator training or tool calibration or replacement. The measurement of the tension of the yarn during winding process will be done using digital tensioner meters. The measurement of the package density of the produced cones after the winding process will be done using package hardness tester. We have used the Sigma XL measurement system analysis. First, we created gauge R&R crossed worksheet for 2 operators and 15 parts with 2 readings per operator per part. The total readings are 60. Then we run the analyze gauge R&R crossed. The results of analyzing the measurement of the yarn tension during winding process using tensioner meters are shown in the table. Gauge R&R ratio is equal to 0.266, which is 7.3%, while variation from machine to another, which is variation due to parts, is 3.384, with percentage 92.7%. No action should be taken for operator training or tool calibration or replacement. The results of analyzing the measurement of the package density of the produced cones after the winding process using package hardness tester. Gauge R&R ratio is equal to 0.00004, which is 4.14%, while variation from machine to another, which is variation due to parts, is 0.00094, with percentage 95.86%. No action should be taken for operator training or tool calibration or replacement. The goal of the analysis, which is to find X's, process and input measures that are leading indicators of the critical output, Y. Such X's are also key to find root causes, the focus of the analyze phase, and to catch problems before they become serious, control phase. For example, for the response or output factor, number of remaining faults per 100 km, with upper specification limit of 3 faults per 100 km, and target of 0 fault, we have 4 factors: number of cuts per 100 km, and bobbin yarn count, and process speed, and also number of yarn breaks per 100 km. The table shows for each response and related factors the upper and lower specification limits and target. Pareto charts are a type of bar chart in which the horizontal axis represents categories rather than a continuous scale. By arranging the bars from largest to smallest, a Pareto chart can help to determine which categories will yield the biggest gains if addressed, and which are only minor contributors to the problem. For each observation, the number of occurrence has been determined in sorting. Then, they have been plotted in Pareto chart. The first table shows occurrence of each observation. The second table shows the Pareto analysis, includes the percentage and percentage of the commutative after sorting the observation criteria according to the percentage. According to the Pareto chart, the variation in actual efficiency percentage, run time, stop time and number of thin places per 100 km are the most categories, which must be controlled. However, the number of cuts per 100 km and density of the produced package are very important categories to be controlled. For each independent variable's x input factor, mentioned in the previous input-output, xy, analysis, we will do the following. Analyzing the collected data and the process limits for each variable. Calculate the process capability and process capability index. The table shows the collected data of number of cut faults in bobbins per 100 kilometers, in addition to the USL of 70 faults per 100 km and LSL of 50 faults per 100 km. Meanwhile, it shows the calculating mean value and standard deviation. The CP is equal to 0.372, while CPK is equal to 0.293. According to number of faults per 100 kilometers, the process is not capable and not centered. We repeat the analysis of process capability indices using Sigma XL. The following report has been generated, which includes the same results. The table shows the collected data for process speed, in addition to the USL of 1,250 meter per minute and LSL of 1,190 meter per minute. Meanwhile, it shows the calculating mean value and standard deviation. The CP is equal to 0.8, and also CPK is equal to 0.8. According to process speed, the process is not capable, but centered. We repeat the analysis of process capability indices using Sigma XL. The following report has been generated, which includes the same results. The table shows the collected data for number of yarn breaks per 100 kilometers. In addition, the USL of 40 breaks per 100 kilometer and LSL of 25 breaks per 100 kilometer. Meanwhile, it shows the calculating mean value and standard deviation. The CP is equal to 1.37, while CPK is equal to 0.83. According to yarn breaks, the process is capable, but not centered. The table shows the collected data for number of weak places per 100 kilometers. In addition, it shows USL of 7 places per 100 km and LSL of 0 places per 100 km. Also, the table shows the calculating mean value and standard deviation. The CP is equal to 0.44 and CPK is equal to 0.3. According to weak places, the process is not capable and not centered. The table shows the collected data for tension of each cone in centinewton with USL of 34 centinewton and LSL of 26 centinewton. Also, it shows the calculating mean value and standard deviation. The CP is equal to 0.45, while CPK is equal to 0.4. According to package tension, the process is not capable, but almost centered. The table shows the collected data for package density with USL of 0.38 gram per cubic centimeter and LSL of 0.32 gram per cubic centimeter. Meanwhile, it shows the calculating mean value and standard deviation. The CP is equal to 2.77 and Cpk is equal to 2.4. According to package density, the process is capable and almost centered. As we noticed from the previous calculations, our process needs to be improved to be capable and centered as possible. For all the required measurements, we used both the online data collection and operator measurement, which collect the results for 100% of production, no need for data sampling. The workflow of our project, which arranged very well in the new mill and new delivered machines. There is no need to be modified because each spinning machine is connecting and supply the winding machine on the same line. The value stream map is used to capture all key flows of work, information, materials in a process and important process metrics. The iGraphX process for Six Sigma software has been used to generate the VSM. The current situation of our mill, as is version, focused on spinning and winding process. It is indicating that the level of whip is 60 bobbins per each winding position, with lead time of 223 hours. The target situation, future version, after reducing the whip between spinning and winding process to only 5 bobbins per winding positions, which resulting in decreasing the total lead time to only 30.5 hours instead of 223 hours. Thank you, and see you in the second lecture of Case Study Module.